Discovery with Mary Lila Grimes, presented by the Lowell Institute Cooperative Broadcasting Council in collaboration with the Children's Museum of Boston and the Massachusetts Audubon Society. And now let's discover about crystals with Mary Lila Grimes.
The snow on your window pane, it's crystals, but we might call it jewels. Jewels of time. Jewels that are born out of just the right amount of time and out of the right temperature. And jewels that are formed from one of the commonest things in the world, water. You know, somewhere above us last night, water vapor cooled at 32 degrees. The atoms of hydrogen and oxygen lined up into thousands of different six-pointed shapes. Snowflakes are beautiful, very beautiful. But what made them this way? What cut out their shape? What cut out their form? The questions about snowflakes are questions about other things, too. For there are minerals and crystals of minerals deep inside the earth. Beautiful crystals, like these crystals of quartz. Square-looking metal cuts, like galena. Beautiful, golden, gleaming crystals like iron pyrite. You know, I think of crystals as being keys. Keys into the very nature of the order of the matter of all the world in which we live. And I think of these keys as going down, reaching to the very tiniest particles into which we can break up everything in the world. But now, before we use these keys, before we read them, don't we need to ask some other questions? Questions about crystals. What are they? What are they made out of? Are crystals minerals? Are minerals crystals? Can a rock be a crystal? We need to go into these things and see what they mean and to see what they are. What is a crystal? An element can be a crystal. Minerals can be crystals. Can a rock be a crystal? Well, in order to answer these questions, I think we've got to look at something that we started with last week. Do you remember what we did? We set up a museum. We started with what we called a rock museum, all the different kinds of rocks of the world. I wonder if you remember this rock. Of course you do. It was granite. We said it was an igneous rock, a rock that was a fire rock. And when we took a close look at it, we said that it was made up of minerals, yes? The white minerals, which we could see, we called feldspar. Do you remember that? And the shiny ones that were clear, we said were quartz. And then the black, we said that that was mica. And that's the rock granite. Now, do you remember how this granite was formed? We said that it was formed deep inside the crust of the earth when a hot, molten liquid that we called magma pushed up into the earth. And this hot, molten liquid, as you remember, cooled. But now, we didn't say too much about what this hot, molten liquid was, did we? You remember that I said it's a mixture of many things. But we didn't go into what this mixture was made of. Now, if I were called on to say to you what this mixture reminds me of, how to describe this magma, I'd have to say that it's made up of elements, as it's everything else in the world. And it reminds me of, well, a pudding or alphabet soup, I guess would be the best way to describe it. For the magma contains elements, which we can represent with their alphabet symbols. Now, there's a possibility of it containing many of the 94 elements which have been found in the earth. Perhaps you recognize some here. Silicon, N for nitrogen, C for calcium, Ma for manganese. Now, this crust, or the upper 30 miles or so of the earth, is primarily made up of 15 elements only. Call them the big 15. They make up 98 1.5% of the Earth's crust. Now, a recipe for this crust. How would it read? Well, take a big quantity of the commonest element, one we don't see, we don't smell, we don't taste, one that's found alone, or it combines with things, oxygen. The next, it's a basic ingredient, 26%, well, 27. It's silicon, an element which is not found alone, but it always is in compounds or combinations. Then comes aluminum, again an element that's combined. Now, a little less iron, the metal without which we couldn't survive in our machine age. Still less calcium. Now go easy with the next ingredient. It's a poison metal, one which combines sometimes with another poison gas to make something you eat every day. Salt. Now add still smaller proportions of the next three. Potassium, magnesium, titanium, and the following. Well, you want to add just a dash of these. First, phosphorus. Then, carbon. That's an element that's found pure by itself, and it combines with other things too. When it's pure, it's diamond. Then, a gas that has the simplest atom in the universe, hydrogen. Then some manganese. Then sulfur. It can be found pure like carbon too. Then chlorine, a poison gas. Now, that's the mighty 15. But you know, we still have 79 elements to choose from for flavoring. You could add 1/4 of 1% of any of the 79 or of many of them. Rare elements like gold or platinum, copper or lead or uranium. And that's your crust. Out of conditions of temperature and heat and cooling, these elements will combine into thousands of different kinds of minerals. The silicon and the oxygen, for example, may combine and produce one of our minerals that we found in granite. Silicon and oxygen combine to produce the quartz, which we found in granite. The potassium and silicon and aluminum may produce mica, and the sodium and the silicon and the aluminum. They might combine and produce other things like feldspar. Now, if these combinations take place in a massive magma, like the one that we just saw, where conditions are crowded, and where each mineral, so to speak, has to compete for space, then it'll result in a rock that looks very much like our granite. See? It's composed of small, well, we'd say the structure is crystalline. For we find that a substance, if it's impossible for it to grow into a full-formed crystal, it'll still develop a crystal form squeezed into the space that it has available to it. But now, you know, somewhere in that mass of magma, the story might have been different. Can you feature a small little cavity or a cavern? It may have been formed in that cooling rock by a gas bubble, a bubble of gas that was trapped and it couldn't escape. Now, that was a perfect environment for something to happen, for the gas and some other element perhaps to combine, and for a mineral form to grow free and to assume its characteristic crystal shape. Silicon and oxygen, when they combine and are allowed to grow free, will produce a quartz crystal, something like that, or like this. See here the beautiful shape of a quartz crystal, which was not crowded in with all the other rocks, but was allowed to develop its form. It's got a characteristic 6 sides here, and then, as it finishes its growth here, it ends off with a little, we call it a pyramidal cap. Now that's quartz. How about the other minerals that we saw in granite? The feldspar and the mica. The feldspar and mica, if they had been allowed to grow free, and they might have developed, say, in a crack that extended out from this magma. and into that crack in an adjoining rock, very rich solutions might have poured. And out of those, we might have had, well, feldspar beginning to form. Now, feldspar has a characteristic crystal, too. It has a shiny luster. Then it has faces which meet at very definite angles. Of course, it isn't as clear and not quite as spectacular as quartz, but it grows to be very big sometimes. One feldspar crystal has been found which filled 2 freight cars with feldspar. It's a very valuable mineral, too. Then the mica. It might have crystallized in the same place. Now, this is a mica crystal. It has 6 sides. And then notice the edges are very rough here. That's characteristic of the mica crystal. Has 2 faces that are shiny, 2 parallel faces that are shiny. Then it has a wonderful quality that you're going to see why in a few moments. Perhaps you can figure out before we get to it. But I can pull this away with my nail or with a knife or sharp instrument. Mica will peel into sheets. Has a very interesting cleavage. And you'll find out the answer to that in a few moments. So we've decided then that crystals are the forms that some minerals will assume. Not all minerals, because some don't crystallize. But most minerals will assume a crystalline form if the conditions are just right when the liquid or when the hot molten mass that they are in cools down, and if they have the right room to grow. So there are lots of ifs, you see. Crystals they're wonderful, but in a way they're sort of miracles too, because you've got to have all the right conditions in order to grow them. But how about our snow crystals? The things that we began with. How did they form? Well, they certainly didn't form inside the earth. They formed in the atmosphere, and the snow had to have just the right conditions, exactly like the quartz and the feldspar and the mica had to have the right conditions. They had to have a fast cooling, a very fast cooling, and we know that the snow crystals formed when the water vapor was frozen and it sort of skipped the liquid state, but they were frozen immediately. Now, they all formed into 6-sided things, too. You'll notice some of them didn't even have to be in points. Some may be solid, like this one. And yet they tell us that though they formed into the 6-sided shapes, that no 2 snow crystals are just exactly alike. That within this basic form, this basic 6-pointed crystalline form, there are many, many variations, as many variations as there are snowflakes. This is true of the crystals of other minerals, too. They vary, though perhaps not to the same degree as the snowflakes certainly do. But they do vary, and you can have a basic form, and yet this form can come out in different ways. Still, it's standard enough, so that scientists, physicists, geologists, people who study the earth, can identify many of the minerals by crystal structure. But now, what makes this? Why do they grow like this? You want to know? I think that's one of the most intriguing questions that you can ask, and the answers are fascinating. Now, I think I can give you some of those answers. Before I do, would you like to see a crystal grow? I've been saying that this happens. Do you believe it? Sometimes we hear things, we read them, but we have to see it to believe, don't we? Well, now, we have set up something, and don't think this is easy either. It might not even work, but we're going to try. We have set up here in the studio a crystal growth. Now, I want you to look at this. This is a compound. Dr. Ed Modest, who is a chemist, has arranged all this for us, and he's starting on it. A compound that's made up of nitrogen, well, 2 nitrogens and carbon and hydrogen. Then it's mixed with water. It's mixed with this amount of water, soluble in water. Then it has been heated, and now it's being cooled by a fan. We heated a solution just like that, and now it's being cooled by a fan. And let's see if you can see the crystals growing and forming. And see what kind of crystalline structure this is going to be. You can see them building up from the bottom of the flask. Now watch very closely. See them? There you see some growing ever so slightly. They got a good start on us. And they're growing into very thin, needle-like structures. This particular compound is. Now, if we had let that grow slower, we would have found that the crystals would have been more perfect. When you have to cool it fast, we used a fan to cool it at a rapid rate so that you could see it. Oh, you can see them building beautifully there now. If we had allowed these to cool at a much slower rate than this, the crystals would have been even more perfect. They would have been even longer than that. Well, now that was fun, wasn't it, to see a crystal grow? But, of course, don't think that you can make one grow that fast, because that's quite a hard task to get it to happen just at the moment. And we even missed part of it here because the timing is very exact. But you can do a similar sort of thing at home. If you use salt and dissolve that in water, in hot water, and then let the water evaporate off in an open dish, after some experimenting, you may be able to grow a salt crystal, sugar, borax, other things. But you can't do them in just a few moments. It takes days to let the evaporation take place in that. Now, back to our question, why did that happen? Why did the crystals of this compound which we were looking at grow into a needle-like form? Why did each atom, so to speak, seem to know just where it should line up and where it should go? Well, the answer to that lies inside the crystal. Now, let's take a crystal. Which one shall we take? How about that? No. Pyrite, we'll look at that later. Feldspar, that's complicated. We'll look at mica, that's quite complicated. Let's start with the quartz. The quartz, which is one of the most beautiful crystals. We've seen how it forms. We saw where it might grow. We saw that quartz is one of the commonest, is the commonest mineral in the world. We found out that quartz in a crystalline form, not in a pure crystal form, is part of granite. Now let's take a look inside of it. I have something here that may represent how a quartz crystal will look. But wait, don't get the idea that what I have here is an exact replica of this quartz crystal, because it isn't. Instead, this is much enlarged representation of the structure of an ultramicroscopic portion of a quartz crystal. Now, you know what all these are, because we went into them last week. We looked inside of an atom, didn't we, and found out that it was particles of energy racing around. And you knew, too, that how big would these be? Oh, about 1/100,000,000th of an inch. So this is way out of proportion. And please remember how much out of proportion it is. But now it's interesting, you know, these compounds, the compound that you saw grow, the compounds that make up the rocks, they're combined of atoms. And atoms have a peculiar property. When they pass by each other or move in orbits close to each other, they may join and act as a unit. This unit which they join in is called a, you know, a molecule. Now, it's interesting that the molecules and the order that they arrange themselves in are exactly what makes our crystal forms. Now, let me show you. You think this is only made up of oxygen by looking at it. But wait. What did you see a moment ago, diagrammed? You saw that oxygen and silicon, the two commonest elements in the world, combine to form quartz. Now, the silicon atom is down in here. Can you see that gleaming there? That represents the silicon atom. Now, the silicon atom is arranged in the center of 4 oxygen atoms. And that arrangement of molecules is always found in the minerals that have oxygen and silicon. It's called the basic of the silicate minerals. Now, look, let me turn it over like this. Now, take a look at that. Let's see if I can arrange it. You begin to see the 6-sided shape. One of them's a little longer than the other, but the 6-sided shape, which is going to result in what? Well, when it crystals, has an opportunity to grow free, it's going to result in that characteristic crystal shape which we saw and which we know as quartz. Now, there are other things that we could look at. Suppose we take a look at another one of those crystals that we saw. One that has a different shape. It hasn't 6 sides. Instead, it's got 4 sides. Now, if we look at that, look at it very closely, you can see that the crystals in this seem to be arranged in cubes. It's called a cubic structure. This is iron pyrite. And you can also see little marks, can't you? Little scratch-looking marks on the sides of these crystal cubes. Now, from what you saw of the quartz and how the quartz molecules were arranged, how do you think the internal arrangements of these different pyrite crystals would be? All right, it would look like this. It's more cubic. And it's interesting, too. Now, what was pyrite made up of? Well, here we had 2 atoms of different elements, again, combining. We have 2 sulfur here and 1 iron. The black represents the iron, and these light represent the sulfur. And when those combine and take on this cubic form, hooked together in this manner, behave as one unit, then we have something like the pyrite developing. It's fascinating, too, that how tightly these are put together, how they're arranged, also determines other things we see in minerals. It determines how hard a mineral is, determines how it breaks. And I can show you that, something very interesting about that, if we look at, well, the next crystal, which I promised to show you something about, the mica. Now, the mica crystal, when we looked at that, you remember, we said that the mica would break into planes. It had 2 flat surfaces, and that it would break into little divisions and planes, and that you would find out why this happens. Now, I think this is the most fascinating of all the ones. And again, when you look at this great big thing, which looks like a cake, please don't get the idea that this is an exact replica of a big piece of mica. Again, it's microscopic representation, so you can see the drama, and see the exciting things that these crystals and that the arrangement of matter means. Now, let's take a look at this, and I love this one, because, oh, it's got everything in it. You see these small balls? Well, those represent aluminum. See that one? And oxygen and hydrogen. The white ones represent the same thing they did in quartz. They were, you remember what? Oxygen. Then we've got our silicon atoms down in here. It's hard to see those, but look, I'll show you something right here. You see this plane here? See this plane that's dark? That's represented by a layer of potassium. And if I take a sheet of mica, split off a layer there, what I'm doing is separating it at this potassium layer, which is weaker than the rest. Now, that's, again, how the internal arrangement of things gives us the characteristics which we see. How do scientists know this? Crystallographers, people who've studied crystals? They know it because they found out that the internal arrangement of these atoms will also show characteristic X-ray patterns, so that they X-ray them and find out things about them. But now, how about our museum? Wouldn't you like to add some of the things to our museum, which we had last week, and look at that? Look at some of the very interesting properties which we see in crystals, too. For instance, this quartz crystal, we'll begin with that because that was the commonest, has a fascinating property. It has a property which, again, has to do with the molecular structure and things about it. A property which, if it weren't for the quartz crystal, you wouldn't be hearing me right now. Because a quartz crystal made into a little thin slice and mounted in something like this glass I have in my hand here is what keeps the frequency of a radio transmitter in operation. So I think it's wonderful, fun to think that if it weren't for a particular property of a crystal, that I wouldn't be even telling you about crystals right now on the air. So we could label that quartz. Then we could add other things to our museum. We want to put in the museum that we started last week, our feldspar, remember that one? Our mica, remember that? How about the one that was made up of sulfur and iron? Pyrite? Now, all of these crystals would be crystals we'd primarily find in the igneous rocks, too, which is what we were working on last week. This is called galena. It's a crystal of lead and sulfur combined. Then, down here, Remember I said that sulfur was one of the elements which would crystallize alone. It doesn't combine. And this is beautiful yellow, by the way, so that's one thing that you miss in not seeing these minerals in color. Then look at this. Crystals don't always have to be square. They don't always have to be cubic or sharp. That's a crystal of iron combined with oxygen. It's an iron oxide. It's called kidney ore. You can see why, can't you? Looks like a kidney. And that's known as hematite. So that's another one of the fascinating kinds of shapes that you could add to a crystal collection. Then look over here. I'm going to pick up something here. We hear a lot about gems. Now that happens to be a crystal of something which, if it were found in a pure form and a clear form, perhaps colored by magnesium, you would know it as a ruby. Colored by another kind of impurity, would be known as a sapphire. That is, let's add it to our museum. By the way, next to diamond, it's almost the hardest thing in the world. That is corundum. So this gives you an idea, just some idea, of the variety of all the kinds of crystals and the fun that you could have with them if you begin to arrange them into a museum as the one we have here. Now think of what we've learned from this museum, from putting it together. We found out last week about rocks. This week we went on to find out that rocks are combined, made up of minerals. And what were minerals made up of? Elements. And we found that sometimes, under the right conditions, the minerals, the elements, can crystallize. And that these crystals are records of the internal order of the atoms and the molecules which act as units. Now, that's the story and common things around you. I hope that you'll discover something about the world of crystals for yourself.
Discovery has been presented by the Lowell Institute Cooperative Broadcasting Council in collaboration with the Children's Museum of Boston and the Massachusetts Audubon Society. Discovery is presented in the studios of WGBH-TV, Boston. This is National Educational Television.